Hello, my name is Kousaku Sato. This is my partner Gopal Paudel. And today, we'd like to discuss about our project, EducaTable. I don't have it. So in this presentation, we'd like to talk about the motivation and the goals behind our project, as well as the hardware and the software. And we will also show the video demonstration of the project. And for the rest of the presentation, we will talk about administrative issues and we will access questions at the very end. So the purpose of our project is to create a new teaching tool for young children from like K to 12 so that they can engage in group activities. And also we wanted to create intuitive interface so that they can use it to enhance their learning skills. The main goal of our project is to create an interactive table that supports multi-touch, multi-user, and the project has to be inexpensive so that the parents and the school can afford it. I'm going to explain how EducaTable works as a multi-touch table. As you can see, input is given by the finger, and LEDs are placed along the edge of the table using the technology called frustrated total internal reflection, which I'm going to discuss in the next slide. As you can see, when the finger is touched on the table, the light gets scattered downwards so that the camera can capture the image and send the data to the image processing. The output of the image processing gets displayed by the projector onto the table. And in this project, it is important for us to have the camera and the projector to work in a different light spectrum. So the reason why that is that we don't want the camera to capture the light coming out from the projector. We also use two mirrors in this project so that the camera and the projector can get the entire image of the table surface. This is a process flow of what I have just described in the previous slide. The one thing I didn't mention is that the camera has to have at least 30 frames per second for the frame rate, in order for us to achieve the real-time feedback. The technology applied in this project is called the frustrated total internal reflection. This technology is very important for our project because the output of the image processing depends on how effectively we can capture the image of the finger touch. As you can see in the picture, the light from the LED goes into the transparent material, and the light reflects internally as long as the incident angle of the beam is greater than the critical angle of the material. And the critical angle is shown here. This technology is called the total internal reflection. But when the finger touches the table, the light from LED at the top of the table surface underneath the finger gets frustrated, so that some portion of the light actually no longer stays inside the material, so which means that the light actually goes out of the material so that the camera can capture that image and send that data to the image processing. And can you go to the slide? Okay, and the reason why it's called frustrated is that the person who invented this had a perspective that the finger touch actually upsets the total internal reflection in a way that the touch makes the light goes out of the viewer, not toward the viewer. And the table surface that we chose for the project is the acrylic sheet. The reason why we chose this is that it's 17 times stronger than the glass. So unlike the glass, when it breaks, it doesn't shatter. So it's very safe for children to use. And also, it works very well with the FTIR technology, which I have just discussed in the previous slide. For the camera, we chose PS3 iCam. It's very inexpensive, and it gives the minimum frame rate that we need. And also, we had to make some modification to the camera. The modification that we made is that we had to remove the in-flat block filter and replace it with a magnetic tape from the flow phases so that it blocks the visible light only takes the infrared light. As you can see in the picture, we use about like 100 infrared LEDs for the illumination inside the table. And as you can see, infrared light is invisible to human eyes. By using the infrared camera, we could actually see the light coming up from the LED on the computer screen. This is the wiring diagram of the LED setup for the FDIR. There's a 100 milliampere current going across each LED. There's a power dissipation of 10 milliwatt in one register. With this setup, we can actually get the full brightness of the LED with the minimum power dissipation, which enable us to avoid overheat. The picture on the left shows the table setup for the FDIR. The image on the right shows the image when we apply 10 fingers on the table. We see the finger as a white blob, and everything else is shown in the black. The projector we chose for this project is a Pico projector. It's lightweight, it's inexpensive compared to the other projectors, and it's not too bright to human eyes. Oh yeah, tracing paper. Yeah, I forgot to mention about the tracing paper. So in order for us to project the image on the table, we had to use the tracing paper, because without that, it just the light goes through the material and show the image on the ceiling. And we also found a nice table frame for our project from IKEA. It's inexpensive. The dimension gives enough space for multi-user, and its height is very suitable for the children to use as a table surface. Gopal is going to take it over from you.
Thank you, Sato. So as Sato explained, we have several different hardware components that make up the physical part of the project. And these components are really necessary, really important in order for the project to function really well. Software is equally crucial part of our design. From the hardware, from the camera, all the computer gets is the image of the table at a certain time. It's all up to the software to process that image in order to give out a sensible output. For the software, we use the C# programming language, and since we had a lot of image processing to do in this project, we used the image processing library called aforge.net that's available for the C# programming language. The core of this software is the blob detection algorithm that's available in the library. What it does is for any image, any grayscale image with a black background, if there is any object in the front, it detects that as a blob, and we can obtain the actual coordinate of that blob and the area inside, all that kind of information that we need to process. So the image coming out of the camera is not always grayscale. So we need to apply a grayscale filtering and then apply a threshold so that we get a perfect black background and all the finger touches appear as blobs or a binary large object in front of the image.